Welcome to this explainer. Okay, so today we're not going to look at the internal combustion engine as just some noisy, greasy metal box. Instead, I really want you to view it as this meticulously choreographed mechanical symphony. You see, every single moving part inside your engine has a specific note to play. And if even one instrument is slightly offbeat, well, the entire performance just falls apart.
Now, it really is a fascinating question when you stop and think about it. How do thousands of violent, fiery explosions happening inside your car every single minute not completely destroy it? The answer is precise, absolute engine synchronization. It's all about timing, right? Managing those explosions so they actually push you forward instead of, blowing the engine to pieces requires a level of mechanical coordination that is literally nothing short of an engineering masterpiece.
Okay, let's dive into this. To really understand the symphony, we have to understand its master metronome. And that magic number, it's 720. In a standard four-stroke engine, 720 degrees of crankshaft rotation, so that's exactly 2 full 360-degree spins, makes up one single complete engine cycle. Basically, everything that happens to generate power in a cylinder must happen within this precise 720-degree window before the whole shebang repeats. And within those 720 degrees, the engine beats out that familiar four-stroke rhythm you probably already know. First, intake to pull in the air and fuel. Then, compression, squeezing it all tight. Next up is power, which forces the piston down. And finally, exhaust, to clear it all out. Up, down, up, down. That's your fundamental rhythm right there. Now, as the piston moves up and down, it hits its two absolute physical boundaries, top dead center, or TDC, and bottom dead center, BDC. These two extremes are absolutely crucial. They're the vital anchor points for our entire 720-degree journey. Every single timing event in the engine is measured relative to exactly where that piston is between TDC and BDC. So let's map this out on a master clock timeline. At 0 degrees, we're at top dead center, and the intake stroke begins. The crankshaft rotates 180 degrees, the piston hits bottom dead center, and boom, compression starts. At 360 degrees, so one full rotation, we're back at top dead center for that massive power stroke. Fast forward to 540 degrees, we hit the bottom again to kick off the exhaust stroke. And finally, at 720 degrees, the piston is right back at top dead center, ready to do the whole thing all over again.
To actually make this happen, we've got two primary mechanical players. The crankshaft is the heavy lifter, right? It controls the violent up and down movement of the pistons and completes 2 full rotations per cycle. But then we have the camshaft. If the crankshaft is the rhythm section, the camshaft plays the melody. It controls the opening and closing of the intake and exhaust valves, letting air in and out like a super precise wind instrument. And this brings us to what is arguably the most vital mathematical relationship in your entire engine, the 2-to-1 ratio. Because the four-stroke cycle requires 2 full rotations of the crankshaft, but the valves only need to open and close once during that entire cycle, the camshaft has to rotate at exactly half the speed of the crankshaft. For every 2 spins of the crank, the cam spins exactly once. If this relationship breaks down, there's no way around it. The engine just fails. So how do we physically lock these 2 spinning shafts together so our mechanical instruments never ever lose their rhythm? Well, engineers use 3 main methods. A timing belt is quiet and super efficient, but, it's rubber, so it eventually needs replacing. A timing chain is metal, bathed in oil, and built to last a whole lot longer. And then for heavy-duty applications, they use interlocking metal timing gears for absolute bulletproof accuracy. But really, whichever method is used, its sole job is preserving that perfect 2-to-1 synchronization. But okay, here's a little secret that separates theory from a real, functioning engine. Everything we just mapped out on our neat little 720-degree timeline, it's kind of a slight lie. In reality, valves almost never open and spark plugs almost never fire exactly at top dead center or bottom dead center. Why? Well, because air has actual physical momentum, and starting a fire takes time. So perfect timing actually requires acting a little early or a little late. And because of that, we get these fascinating engineering tricks, like valve overlap. There's this brief, intentional moment at the very top of the exhaust stroke, where the exhaust valve hasn't quite closed yet, but the intake valve has already started to pop open. Yes, both are open at the exact same time. I know it sounds like a mistake, but it's actually brilliant. The rapidly exiting exhaust gases create this vacuum that literally pulls the fresh air in behind it. This process is called scavenging, and it drastically improves the engine's ability to breathe. Now,
What's really interesting here is that we're actually dealing with two entirely different types of timing happening simultaneously. Valve timing controls the engine's breathing, the physical opening and closing of those metal doors. Ignition timing, on the other hand, controls combustion initiation, the exact millisecond that the spark plug fires. They're totally separate events, yet both absolutely must be perfectly synchronized to the master clock of the crankshaft. Let's take a closer look at that ignition timing, because it takes a tiny fraction of a second for the flame to actually travel across the cylinder. If you wait until the piston is exactly at top dead center to fire the spark, you're already too late. The piston is going to be moving down before the explosion even peaks. So we use something called ignition advance. We fire the spark slightly before the piston reaches the top. That way, the maximum pressure wave hits exactly when the piston starts its downward power stroke.
Back in the old days, mechanical distributors had to handle all of this. But today we have a digital conductor, the engine control unit, or the ECU. Think of it as the electronic brain that's constantly calculating and adjusting both the ignition and valve timing, literally thousands of times a second. It reads data in real time, adapting the timing based on how fast you're driving, how hard you're mashing the gas pedal, and even the temperature outside. And to pull off this high-speed juggling act, the ECU relies on a whole army of sensors acting as its eyes and ears. It watches the throttle, it measures the incoming air, it sniffs the exhaust. But the two absolute most critical pieces of data, those come from the crankshaft position sensor and the camshaft position sensor. These two sensors tell the computer exactly where the engine's mechanical parts are at any given microsecond. But you might be wondering, if the crankshaft is the master clock, why do we even need a sensor on the camshaft? Well, remember our 720-degree cycle. The crankshaft spins twice. So if the crank sensor says the piston is at top dead center, the ECU doesn't actually know if it's the top dead center of the intake stroke or the top dead center of the power stroke. The camshaft sensor, spinning only once per cycle, completely solves that riddle. It tells the ECU exactly which half of the cycle that specific cylinder is in. Because the ECU has this incredibly precise data, modern engines can perform magic tricks like variable valve timing. In older engines, valve timing was pretty much fixed, just a compromise between idling smoothly and driving fast. But variable valve timing uses oil pressure to physically rotate the camshaft slightly while the engine is actually running. This literally changes the engine's breathing rhythm on the fly, optimizing it perfectly whether you're just sitting at a red light or totally flooring it onto the highway. Now, if you're driving a diesel, your engine plays a slightly different tune in this symphony. You see, diesels don't actually use spark plugs. Instead, they squeeze the air so incredibly tight during the compression stroke that it becomes superheated. Timing in a diesel engine relies entirely on the ECU injecting the fuel into that superheated air at the exact right microsecond. The fuel just naturally ignites itself right on contact. So we've got this beautifully complex 720-degree dance happening thousands of times a minute. But what happens if this mechanical symphony falls out of sync? Like, what if the timing chain stretches, or worse, the timing belt completely snaps? Well, the consequences of getting this wrong range from, let's say, highly annoying to absolutely catastrophic. Look, if the timing belt skips even a single tooth, the camshaft and crankshaft are no longer aligned, and the driver is going to know immediately that something is very wrong. We're talking rough idles, intense misfires, a massive loss of power, and backfiring because fuel is igniting while valves are wide open, all topped off by a flashing check engine light. And if the timing is too far off, the engine simply will not start at all.
But the true nightmare scenario, that occurs in what's known as an interference engine. In this specific design, the valves open so deeply into the cylinder that they actually occupy the exact same physical space the piston does when it reaches top dead center. They never touch because of our master timing synchronization. But if the timing belt breaks, the camshaft stops, the valves get stuck open, and the crankshaft just keeps pushing those pistons violently upward. They physically crash into each other, bending metal and literally destroying the engine in an instant. So the crucial point here is that engine timing is never just about one single event. It is the flawless, ongoing coordination of three distinct pillars: the physical position of the piston, driven by the crankshaft, the opening and closing of the valves, directed by the camshaft, and the exact millisecond of combustion, controlled by the digital brain of the ECU. When you turn the key in your ignition, you aren't just starting up a simple machine. You're kicking off a continuous 720-degree masterpiece of mechanics and physics. Next time you hit that gas pedal, I really hope you can visualize that incredible high-speed symphony happening right under your hood. It makes you wonder, doesn't it? Is your engine's clock ticking in perfect harmony? Thanks so much for joining me for this explainer, and keep learning.